Is this good? Testing? Not loud enough? Okay. So I'm going to speak on embedded trivalent graphs and their algebra. Or if you know what subtitle means, then this will also make you happy. But if you don't worry, it won't be necessary. So at this point, I'm supposed to tell an amusing story about when I first met Dennis, but of course I can't do this because I don't know how I'll remember when I first met Dennis. And I'd also like to take a moment to thank my sponsors for this talk and give a message from our sponsors. Use Try's Shadow World. Describe your four-manifold with two-dimensional polyhedra. In fact, this entire talk you can think of as an advertisement for Try's Shadow World. This was paid for by Polio Rashid. So let me start off by. So knot theory is usually done by looking at a planar diagram of a knot, like this. So there are two knots. There are other ways of representing knots. You might represent them with what's called a non-associative tangle, which means that you, in addition to having a two-dimensional projection, you then have a one-dimensional slicing indicated by these dotted lines. And in each one-dimensional slice, one thing happens. There's a critical point, or maybe there's a reassociation here, or a rig. But I don't like these pictures. Knots are really three-dimensional objects, and these pictures are doing a great violence to a knot by taking a three-dimensional object and squashing it down into a plane, or even worse, onto a line. So we'll try to do better in this talk. Another point about knot theory is that there just aren't very many things you can do with knots, or rather, there are many things you can do with knots, but they all land in very special classes of knots. You can do connected sum, cabling, and satellite, but the image is always a very special type of knot. So in this talk, I'm going to look at embedded trivalent graphs. So if instead of looking at an embedding of a circle, you look at an embedding of a more general one complex, some arbitrary graph, I'll just restrict to trivalent graphs, but there's not any particular reason. Then you have many more operations. So as for knots, you have a notion of connected sum. If you have two separate embeddings of trivalent graphs, then you can take the connected sum along an edge, get a new edge, get a new diagram. And this is well defined as long as there is a separating two-sphere, as long as they're really separate graphs. If you have an edge like this, you can imagine you have a zipper along here, and you can unzip the zipper, and you end up with two components there. Or you can add a little. There are various other things you can do, but these operations will be enough. And let me emphasize that these are all, first of all, these are all three-dimensional. These are all well-defined three-dimensional operations, unlike, say, changing and crossing in a knot diagram. Which is something people often talk about. If you change and crossing in a knot diagram, you really are making an additional choice on top of your knot of which crossing you're picking. These are more intrinsically three-dimensional. The only one that's not obvious that it's well-defined is the connected sum, and the proof there is exactly the same as the proof for knots. You can shrink one of these graphs down very small and slide it along, and slide it along there are. And just to make me explicit, so all knots for sigma unzip to be well defined, your knots and graphs have to be framed with half-integer framing. So here are some example identities with framed knots. So this one might not be so obvious to everyone, so I've prepared some models of this, which I'll pass around. Prepared some proofs of this, which I'll pass around. So I've taken an unknotted theta graph, like so, and deformed it into this embedding. And this is, so again, I'd like to thank Collier Russian for this sponsorship money, which is being used well. So, well, okay. So we have these moves, the unzip, connected sum, and so forth. And so the first thing that we notice, this is good. One goal is to try to describe knot theory by generators and relations. So with these moves, knot theory is generated by a planar tetrahedron, and a Mobius strip, a positive and negative Mobius strip. So, so for the proof, first there are some additional moves you can do. You can do, if you have two vertices of in two separate trivalent graphs, the same conditions for a regular connected sum, but you can first do a connected sum along an edge, joining the vertex, and then do an unzip, and you've ended up deleting a neighborhood of the two vertices and merging them together into a little three-lane highway. And furthermore, just by taking the connected sum with the Mobius band, you can change the framing along any edge. And this is the only thing, exactly what we use the Mobius band for. And so this is, and other than that, we can forget about it.
What do you mean by that?
I want you to really think of these as embeddings of little ribbons. So, I mean, and the ribbon has two edges which can join up to itself with a twist. Okay?
What does that mean?
Half integer, well, this is a 1/2 framed knot.
Oh, okay.
Yeah, I'll just do that in a second. Okay. So it's a little exercise to check that this tetrahedron here is just the standard tetrahedron with some change of framings, with some half integer change of framings. So now we want to prove that you can generate any knot. So you can start with a knot. Start with a knot diagram, like this trefoil here, and this is going to use the well, any embedded trivalent graph as well. No. Any embedded trivalent graph can be generated, as well as, but in particular knots. So for instance, a trefoil knot. So we're going to generate this using our generators in relation, using the domino theory. You know, this theory that where the blue lines represent the blueprint of the knot, and then the red are how we're going to conquer the world. So first we have a tetrahedron at each of the vertices. That's just one of our generators. Then we can do a connected sum along this edge, because they're disjoint tetrahedra, ending up with this part here. And then we can again do the connected sum along here, ending up with this diagram here. Now we might want to do a vertex connect sum along here, but remember this is not well defined because these vertices are in the same component.
Well, can you please explain what you're doing? You're starting with what?
I'm proving that that every knot can be is in the algebra generated by these elements.
And so what's the knot you're generating now?
The trefoil.
Okay.
Okay. Meaning that so the moves, the unzip, the unzip, and the connected sum principally. Right. So, which are a special case of embedded trivalent graphs. So really, I should probably say. On the right. Oh, Mobius strips. I'm sorry. I should have pointed this out at the bottom. This is a convenient notation for a Mobius strip. Instead of drawing an explicit ribbon like that, you just draw where the family changes.
We use blackboard framing
Yeah.
when you have the
Exactly.
direction.
Exactly. So with the unzip and question. There aren't any vertices. So it's not. So properly, I don't want to consider graphs. I want to consider one-dimensional polyhedra. I mean, spaces that locally look either like a line or like a trivalent vertex. Right.
You're at the point where you're not allowed to unzip along that.
Right. So I did the vertex connect sum here and here, which I was allowed to do because I had two. I was just starting with abstractly three tetrahedra, and abstractly I'm allowed to do this vertex connect sums here, and I'm not allowed to do this vertex connect sum here. Instead, what I can do.
So you're creating out of the three grid generates there, the grid.
Exactly.
Yeah.
Exactly. I'm starting with the red things and taking over all the blue regions and generating more and more. So it's one of our generators. It's one of the generators. I start with
He took the trefoil knot that he wants to get.
Okay, so the trefoil knot is pure blue.
the trifoil knot.
It's not growing. And somehow you
No, what really exists is that you get and the blue lines are only there to help you visualize what is it, what it's trying to do.
The blue lines are a blueprint for what I want to do.
The blue lines aren't really there.
Right, and so I start with only my three generators. I do these vertex connect sum. Then I can't do another vertex connect sum, but instead what I can do is I can slide this edge from here over to here, like so, ending up with this diagram here, and then then I can do an unzip move there. And so,
We
around.
slide the whole graph, the whole slide out so we can see.
Oh, thank you. So then I can do an unzip move here, and then I can follow this by I can slide this edge over here, this edge over here, this edge over here, and then do unzips along all of them, and I get what I wanted: the trefoil plus, unfortunately, an additional component, an unknot, which I guess. Well, there are two ways you can deal with it. Either you can trace back exactly which edges were giving you this unknot and delete them from our generators and end up with little theta graphs instead of tetrahedra, or we can allow another generator dropping an edge. But in any case, with a little more work, we can get rid of this extra unknot. Is that okay? Sorry, can you say that louder? No. So see, so the question was whether I can take the unknot away from the trefoil and then do a connecting sum. And the answer is no. I mean, because I don't, I mean, even though the unknot is in fact separated from the trefoil, I don't have an exhibit of that fact. I'm only allowed to do connect sum between trivalent graphs I've generated separately. Yeah. So, for instance, so if I had started not with a not a tetrahedron, but with some other tetrahedron, embedding of a tetrahedron, then this extra component would be linked with, would probably be linked with. Well, with any possible configuration, I can do a move and generate some knot. It won't be the trefoil line generator. Right. So if we want to do knot theory by generators and relations, of course, we should look at what relations we have. So there are some. So here's one relation, which is, you can think of this is very much like the usual relation that if you join two tetrahedra, you can decompose it into three tetrahedra. So here, except this is the dual picture. So with two tetrahedra here, we can take the vertex next sum and get a triangular prism. Or with three tetrahedra here, we can do we can do the same thing we were doing with the trefoil. We can take the vertex down sum here and here, get this picture, and then do an unzip move and get a triangular prism looking a little bit different, but it's the same, in fact, the same framed triangular prism. And these two are the same embedded trivalent graph. And but this relation only involves the tetrahedron, and of course we need some relation which involves the framing as well. And it's here. Basically, you can put together two tetrahedra in such a way that you get a single tetrahedron. So, well, these are the important relations. There might be more relations, but they're not going to be so important. But this is an unzip. And the reason it comes out twisted is because of this half framing twist here. Well, here I've done a connected sum with a Mobius strip, and no, I just did a single unzip, and the new edges come out twisted. There's no way to unzip this.
What's the second arrow?
The second arrow is change framing. The unzip depends on depends only on the choice of edge though, and it's determined by the framing. I guess I should be more specific along this edge. Right, that's part of the algebra is the choice of the edge. Right. So I mean, but this is the real question though. What is the algebra? If these are generators and relations, but it's actually not so obvious what the algebra is. For instance, if I took three arbitrary embeddings of the tetrahedron up here, then it turns out, and then I did these two vertex connect sums, and then I did an unzip. The answer is independent of, and compare it to doing the vertex connect sums at a different two vertices initially, and then doing an unzip. So then the answer is independent of the order in which I did it. This is, well, I don't know. It wasn't obvious. It's not obvious. It wasn't obvious to me, but it's true. Maybe I'll just sketch a little proof of that. So I have some. If I have some embedding of a tetrahedron here. I guess I should make it. Is that a tetrahedron? Yes. So this can be arbitrarily knotted, but we can always arrange it so that we have this little subtree here, which we can arrange to be embedded straightly, and we have another little subdivision here embedded somehow. And again, we can arrange for this part to be embedded straightly. And same down here. And then if we study exactly what happens when we do these vertex connect sums and unzips, we end up just taking these three and joining them up straight. I mean, in a sort of standard way. So that's a sketch, but you can complete that if you want. I mean, for non-standard tetrahedra, this won't be the standard triangular prism, but it will be independent of the order in which I did these operations. So this is the question. What is the algebra that we're combining these trivalent graphs with? So let me convince you that this is a good question by telling you a few other spaces that satisfy these exact same operations. First, was in John Baez's talk this morning. The L2 of the space of connections on your graph modulo gauge equivalence. And then, I guess, for those who know the theory of finite type invariance, there's another. Well, I guess there's an analog of these connections, group value connections. There's an analog with Lie algebra, and then for any, and then there's a universal version, which is some chord diagrams. So you place certain trivalent graphs on top of your original ones and mod out quotient by some relations. Which, well, I'm just mentioning that because so these are some other spaces that satisfy the same operations. And to convince you that the operations are non-trivial, let me tell you two different shadows of this, two different pieces, very special cases of these trivalent graph operations. So one is that it is called non-associative tangles. So this is a picture I had on the first slide. So you're starting now with, so a non-associative tangle is just an embedding. It's a tangle, so an embedding of some intervals and circles into space with some top and bottom, and then the top and bottom are both parenthesized. So these two are close and these two are close, whereas here, these two are parenthesized, and then this is parenthesized with this one, and then the whole thing is parenthesized. So we can turn such a non-associative tangle into an embedded trivalent graph by drawing a tree corresponding to the parenthesization. And in fact, so embedded trivalent graphs with a distinguished rooted spanning tree are equivalent to non-associative tangles. And as with non-associative tangles, there's a natural multiplication, just stacking one on top of each other. And you can realize this multiplication easily in terms of these operations. So as an exercise, for instance, you can check that the pentagon identity in category theory, which also appears in non-associative tangles, like this, just the different ways of parenthesizing four characters from all parenthesized to the left to parenthesized to the right in two different ways. That this is equivalent to the pentagon equation that I wrote earlier. And I guess the point here is that a single associator, when you use this equivalence, turns into a tetrahedron. So that one is actually not so hard to understand, but there are some other appearances that are slightly more mysterious. So a planar algebra is some collection of spaces, one for each n, corresponding to the number, that can be connected up with planar diagrams like this, where, so here you would take an input in the fifth space for these 5 strands coming out, one in the fourth space for these 4, another one in the 4, and get something in the fifth space. So, so I claim that an embedded trivalent graph with a distinguished cycle form a planar algebra. So, to better understand this, let me first, yes? This is not quite the version of planar algebra that Von Jones has. Fine. That's your question. But I think this is the better definition. Yes?
Maybe you could again, what does this mean for TG?
Trivalent graph.
And ETG.
Embedded trivalent graph. Exactly. So the question was, the comment was that the inner circles are the input and the outer circle is an output. It's an operand where these are the inputs and this one's the output. And you can, the operation is just nesting them inside each other. If you have another, for instance, we could take this whole diagram and nest it inside of this one here.
Are we supposed to know what planar algebra is on the basis of this?
So this is not a precise definition, but this is.
Because it didn't work for me. I said, no,
So, I mean, again, this is not. So,
What do those red lines represent?
the red lines are the planar algebra, are part of the data of the planar algebra. So let me give you an example of a planar algebra that might. So an example of a planar algebra that you can easily understand is that if inside of is planar tangles. So if inside each of these circles I put some tangle like this, then and I guess I have to some tangles. It doesn't matter which ones. So sorry, a planar tangle. I mean,
Is such
sorry.
a thing as a template for an operation? The thing that you can stick inside a lot of things, like
Right.
like
They-
a
so-
template, instead of template, that a term structure called operator.
Right. So again, the red lines on the outside of these circles are a template for operations that you can perform. And so, for instance, if you had if you have tangles inside each of one of these, you can then perform an operation, connect them up as indicated here, and get some larger tangle. No. Guidelines for plugging things in. Don't worry too much because this is not. You don't need to understand this to understand most of the talk. So this is well defined for ordinary tangles. So, but the remarkable fact is that we can make this. This is well defined for an arbitrary embedded trivalent graph, where we take the planar tangle and draw a circle around it. And we can look at an arbitrary embedding of these graphs here, and these operations will still be well defined. So for instance, the simplest case would be when a special case of a planar algebra is when you have none of these red lines at all. You need to specify how you're plugging in your objects. Yes, you need some kind of base point if you want to be precise, which I don't want to be. So for if you consider the case where you have no red lines at all, then this is some operation which takes 3 inputs, each an embedded trivalent graph with a distinguished cycle. So an embedded trivalent graph with a distinguished cycle which has no vertices on it. So that's just a knot, possibly with something else in this complement, but mostly just a knot. And then you're getting something else, another knot as the output. And this operation is one natural operation, which is the connected sum of knots. So, right. So this is not such an easy exercise, but you can think about this if you're a topologist and you're bored with the rest of the talk, to give a nice topological description of this operation. So those are some examples of what we can do with this algebra. But let me now tell you. Let me now switch to giving you the complete description of what this algebra of operations you can do is. So an operation, remember, I mean, it's some sort of combination of unzip and connected sum and so forth. And so we want to describe the space of such operations, which makes obvious equalities obvious. And it turns out the correct description is to think about you have some graphs as input and some graphs as input and graphs as output. And the correct description will involve a 2 complex whose boundary is the union of the input and the output. So let me give you some examples of such 2 complexes before I give the actual construction. So, for instance, to do an unzip loop, we want some 2 complex whose boundary is this space on the bottom, this one on the top, and there's a very natural 2 complex to write down, which is this one. We have a little bygone region here, and you've split apart. You split it apart. Or here's another one, the connected sum. You start off with this portion of a graph at the bottom, of 2, I guess, this portion of 2 graphs at the bottom, this portion of a single graph at the top, and then there's again a natural cobordism between the graphs at input and graphs at output. So here's a more complicated example. This is the 3-sided pentagon, which, remember, involved taking these 3 tetrahedra, doing unzips, vertex and exons here and here, and then doing an unzip to end up with this picture. And this is the appropriate 2 complex. Again, here, so these 3 boundary components are the input, and this outer red boundary here. All the red components are input, either input or output. The outer one is the output. These 3 are the input, and there's a particular 2 complex which co-bounds them. This is an abstraction complex which is not embedded anywhere. Yeah.
How do you interpret this restriction on when can you make the connected sum, for instance?
Right, so this will be a certain restriction on the topology of this 2 complex. I'm going to say it a bit. Well, it's that. Let me put it this way. The restriction is that so you have this identification of the boundary of this the two complex with the union of the inputs and the outputs, and the restriction is that when you take this your two complex and union with the cone over all the input graphs, the result is contractible. So
Can we go back to that picture a minute, the fancy picture?
the fancy one, okay?
That picture seems to has pretty full symmetry. Is that an illusion or not?
It does. It does, yes. And this is a good thing. That, the way we constructed it originally do not have the symmetry, but now we do have the symmetry, which exposes the true symmetry, underlying symmetry of this operation. And you notice that again, here, if we cone over the three inputs, then we end up with some contractible complex. And for the connected sum here, if these two pieces were of the same component, then when we coned them over, we would end up creating a little loop. Yeah. Some genus. Yes?
Just to make sure I understand, when you talk about the boundary of the two complex, you mean the set of edges of degree 1?
So these two complexes are, they're locally either like a portion of the upper half plane or the R plus cross a tripod. And so the boundary are these pieces that are locally like the boundary, the edges there. I guess the picture's not so clear. I mean, the black edges are not edges, they're just there to make the picture drawable. Yes. So let me be a little more explicit about how we construct an operation. So given the two complex, how do we construct an operation on trivalent graphs? So the idea is to find some three manifold which co-balance that will glue into our original three manifold to get a new one. Sorry, let me say that again. We start with some three manifold with an embedded trivalent graph. If we remove the neighborhood of the embedded trivalent graph, we get some three manifold with boundary. Boundary is some handle body. Then I'm going to construct a three manifold whose boundary is part of his boundary is that original handle body, and part of his boundary is some new handle body, and this will and I'll glue the part that's the original boundary in to get a new manifold with boundary, which will be, and with appropriate restrictions, the new manifold will still be the complement of an embedded graph in S3. So that's a little hard to visualize. So let me go down one dimension just to, because it's easier. That's easier to visualize. This was actually related to Sasha Krylov's talk. So given any graph, we can construct a surface from it just by taking a little circle bundle over each edge and a little theta over each vertex. So we should be careful that this is. There are other ways to construct surfaces from graphs. For instance, you can thicken your graph a little bit and form a little flat graph. And this is not what I want to do. Instead of taking an interval bundle over the edge, I want to take a circle bundle. The other comment is that this is equivalent to embedding your graph in R3 or in any three manifold, however you want, and taking a little regular neighborhood of it. So we're going to do the same thing with two complexes, except instead of embedding in 3 dimensions, we'll embed them in 4 dimensions. So there's one additional little twist, which is that now a circle bundle over it does depend a little bit on embedding. A circle bundle over a 2 cell has a Turing class, which we need to record. So we'll record that with either an integer or half integer over each 2 cell, and then again, a theta over each edge, and the join of 4 points and 2 points over each vertex. Turns out to be the right thing. And I should comment here that these now, I'm including my generators in the algebra now. So the Mobius strip, of course, will be the same as this data of which bundle you have. The Mobius strip is essentially changing which circle bundle you have, and the tetrahedron is what you get in the neighborhood of the vertex. So, but let's include the Mobius strip and tetrahedron in the algebra for the moment. Well, sorry. Before I do that, let me give you some examples where we can explicitly see what this 3-manifold is. So the first example is cabling. So first, the 2 complex. We want the 2 complex with boundary, 1 circle input and 2 circles output. This is the right 2 complex. And the 3-manifold. And on the other hand, to cable a knot, you can think of it as taking the torus, which is boundary is the knot, and gluing in one of these gadgets, a solid torus with 2 solid tori inside it removed. And then we're supposed to see this. We're supposed to be able to see this solid torus with 2 solid tori removed as a regular neighborhood of this graph, and as the boundary of a regular neighborhood of this graph, or mostly as a circle bundle over this 2 complex, except for some special behavior along the edge here. So I sketched that here. Here are the circle. Here we can decompose this this gadget into the union of 3 annuli cross S1, all of which are floated by circles. So these are the red circles that are running around here. And then the special fiber is this theta graph here, which is lying over that one here. Just another example, which is somewhat harder to see. So to form the connected sum of knots, you're taking 2 manifolds with torus boundary, and you're producing another manifold with torus boundary. And it turns out that you're actually gluing exactly the same gadget in, except with some different, except you're looking at it in a twisted way, where now you're thinking about this direction as the meridian. And you can see, so this corresponds to, you can see this bundle as a circle bundle over a pair of pants here. It's just a pair of pants. This is just a pair of pants process 1. So let me so now if we include the Mobius strip and the tetrahedron in the algebra, we're now looking at general I guess 2 complex is actually slightly wrong, but fake surface is better because the 2 cells need not be, the 2-dimensional objects need not be cells, need not be contractible. So this is a representation of knots that generalizes both knot diagrams and non-associative tangle representations. So every contractible integer shadowed fake surface with boundary determines an embedded trivalent graph. So this integer shadowed is triassociation. These are just these integers or half integers that we put on the 2 cells. So the proof, for the proof that for any contractible surface you get an embedded trivalent graph, you just take an arbitrary embedding of this fake surface in some 4 manifold, doesn't matter which, with the appropriate, obeying the appropriate conditions on the two cells, with appropriate trig class on the two cells, then because it's contractible, the regular neighborhood will be a 4-ball, and the boundary of the 4-ball will be a 3-sphere. And then by looking at what was happening to the boundary of your surface, you get a trivalent graph. So, so on the one hand, we get embedded trivalent graphs this way. On the other hand, we can get any trivalent graph this way. And in fact, I've already proved this. So this is just the fact that any knot can be generated using these operations. So I have just drawn the same example that we had before here, which was generating the trivalent knot, and this is the right 2 complex. So these lines here, so this 2 complex is not embedded in 3 space. So there are some fake intersections which are drawn with these dotted black lines here. But otherwise, this is a correct 2 complex whose boundary is a single circle, and the pluses and minuses are indicating these frameworks. So, and again, I should say that this is all. These pictures are all really Drive's pictures, who is, I guess, considering them in somewhat different contexts. So the approximate theorem is that knot theory is generated by generators and relations from the tetrahedron and Mobius strip with the relations on the pentagon, the hexagon, and some cancellation, these roots on complexes. And this bottom one here is again not embedded. You're changing this attaching curve here and having it go over the extra component while introducing some things. And it's an approximate theorem because it's not quite true, because there's a few conditions that are missing. So, well, I realized this after I had drawn these slides. For instance, the unknot can be represented just as the boundary of a disk. If you take a single disk and do this construction there, then you get an unknot. And on the other hand, all of these relations involve. So, but the problem with unknot is that there are no singular points of any of these kinds, and all of these relations involve singularities both before and after. So you need some additional relation to deal with the unknot. Yeah. The bubble move. Just let me just try. So you want to go from add a little bubble into an edge, and the surface is this one. So, those operations, those generators, those operations are sort of special to embedded knots, and so these other spaces of associated trivalent graphs don't have a natural vertex the way that knots do. So in general, the operations that are naturally defined for setting connections on a graph are specified, specified by a more restricted set where we forbid vertices and we require all the integers, all the associated integers, gleams, or whatever calls them, to be 0. So that's about all I have to say. Let me mention some, why I'm interested in this. So first, I kind of like this way of describing knots. It's some somewhat more geometric way of describing knots than a knot diagram. So I'd like to think about them just purely topologically and try to study, say, the minimal number of vertices that you need to represent particular knots and whether that has some nice geometric significance. So it would be nice to give an extension of this description to three manifolds, which is it's close to true, but it's not quite true. So it can't be true that so every three manifold can indeed be represented this way, because just removing the topological restrictions on the two complex. The reason is that just by attaching a disk to one of our circle boundary components corresponds to performing surgery on that knot. So we can represent any link, and then we can do surgery on the link to get any three manifold. But this clearly will not be enough to. The moves are clearly not sufficient because because instead of taking the circle bundle, we could have taken a disk bundle as well. That was another well-defined object, and we would get a four manifold whose boundary is the three manifold, and that is preserved by all of the moves. So we need some additional moves which change the four manifold. You can compare this to the situation in two dimensions, where where you have some moves that correspond to some surfaces, in particular the I to H move. But these are not enough because these you need the S move on the torus in order to change the three manifold, which is found in the two manifold. Is one way to say that. I guess here this is the original reason we were thinking about this is that Dror and I wanted a better proof that Vassiliev invariants exist. So there's a sort of cohomological proof using these non-associative tangles where you construct an associator step by step. But this is unsatisfactory because it's really missing much of the geometry of the knot. So the way to think about this is that quantization is to quantize, or you're going to construct some element of in one of these two spaces on the right, which is the image of the tetrahedron in embedded trigonal graphs. So satisfies the identities. And I guess then the immediate problem is how to, so then to do the same step-by-step procedure that works for non-associative tangles, you have to know what the relations between the relations are. And I guess I can probably write them down. I don't know how to prove that they are now. And I guess it would also, so these relations and relations between relations are sort of ascending in hierarchy. You can think of the relations as being related to certain three-dimensional polyhedra, sort of three complexes with, again, disk bundles over them. And it'll be interesting to try to see how far you can push this through. Thank you very much. Dror has written a fairly combinatorial proof for the division of this color in Grindel. But it's not, excuse me, again, it's not very topological. It's not very topological. Not yet.
Say how the
about sort of L2 on each?
Sure. Sure. So, well, so some of the operations are easy. So, for instance, for an unzip.
What question are you answering?
Sorry, the question was how does L2 of gauge classes of connections inherit the same structure? So, so for the unzip, for instance, we want to start with a gauge class of connection here and then a gauge class of connection here. And since we have a map, there's a natural map of the associated graphs from here to here. Just, an obvious map. And we can just pull back the connection by that map. Similarly, for the bubble, we can do the same thing. It's a little, so for the connected sum, it's somewhat more complicated. So let me just say what it is for the case of connected sum of knots. It works the same in general. So for knots, the connections modulo gauge equivalents are just conjugates of classes on the group, and then this operation on L2 of the space here is convolution of the two functions. I should mention that when you do this quantization here, in fact, it's a map not to this. This is a sort of standard trigonal TG algebra structure on these connections, and the image here uses a somewhat a twisted structure, but the twisting is fairly easy to describe.
Any further